Rather than giving you a full account of Detector, this tutorial exposes you to the core ideas of the tool. I will explain the mechanics of Detector and the workflow that you should adopt to get started. The tutorial webpage is designed to give you a more comprehensive account, and I suggest that you consult that if you need further details. I also recommend that you give the tutorial paper a quick look, since it complements some of the concepts covered here. You'll find links to these two resources in the video description below. Going forward, I will assume that you have installed Erlang on your system. You'll find the full instructions on how to do so on the tutorial website in the section entitled Preparation under the heading Getting Started. Once you complete the installation, follow the rest of the instructions to download and compile Detector. Ideally, you went through the quick start and managed to make it work. But if not, don't worry, installing Erlang and compiling Detector should be enough for this tutorial. This presentation is delivered in 3 parts. In the first part, we dive right in and look at an example program and try to get an idea of what programs we might want to runtime verify. As a byproduct of this exposition, you'll familiarize yourselves with the basics of the Erlang language and with the basic concepts required to operate the Erlang shell. We also go over certain safety properties that we might want our program to observe. In the second part, we formalize these properties in SHML, which is the logic Detector uses. We spend some time detailing aspects of this logic and discuss that despite the limits of the runtime setting, we are still in a position to be able to monitor for useful safety properties about programs. In the last part, we get down to the business of generating analyzers from SHML formalizations of such properties. We showcase inline and outline instrumentation and demonstrate how these can be employed to monitor programs that are subject to specific deployment and runtime constraints. Now, let's begin. Let us start by getting familiar with the kind of programs that we will be dealing with. So you already got a taster of a simple program for our Hello World example from the tutorial website. And that program, if you recall, consisted of a single process that writes Hello World to the Erlang shell and then exits. Now we'll look at a more realistic, albeit smaller example of this paradigm, where processes communicate with one another via asynchronous messages. Let's consider this example of a calculator program that consists of one process. The two important functions here are the start function and the loop function. The start function spawns the calculator process. Spawn takes 3 arguments that are the name of the module where the function that we want to spawn lives in, the name of the function as an atom, and the list of arguments the function accepts. Our function start here is parameterized by the number n, and this number we use to keep track of the number of requests serviced by the server. We simply pass this value n through to the list of arguments that loop takes. Let's move on to the calculator server process loop. So processes in Erlang, also known as actors, are concurrent entities where each process owns a message buffer called the mailbox. This message buffer is used by actors wanting to communicate with our current actor process. Actors communicate by depositing messages to an actor mailbox in a non-blocking fashion, which the recipient actor can then read at a later stage. To take messages out of this mailbox, an actor uses the receive expression shown here. And what this receive does is it takes out a message and then pattern matches it with a number of clauses. In this case, we have 3 clauses, which correspond to the requests that our calculator server is able to handle. When the pattern match succeeds, the receive executes the body of the matched receive clause. A pattern match is successful when the shape of the data and the shape of the pattern coincide. Upon a pattern match, the unbound variables in the pattern become instantiated with the actual data values contained in the message. Variables in Erlang are written with a capital letter. So for example, CLT here is a variable, A is a variable, B is a variable, and so on. In this case here, we're saying that receive takes out a message and matches it to one that has this form, a pair consisting of the client PID and the payload. The client PID is the PID of the process that issued the message to our calculator server. Internally, the payload is made up of three elements: the add atom, the value A, and the value B. So, as you might have guessed from this pattern, this message represents an add operation that we would like our server to carry out for us. Suppose we receive an add operation. What do we do then? We compute the addition of A and B and wrap it in another tuple that consists of two elements, the atom OK and the result of the addition. And we call these atoms at the beginning of tuples tags. Tags are basically a convention that Erlang programmers use to describe the nature of the data in tuples and what it represents. How do we handle the add request? Well, we send a reply message that contains the result of our computation to the client. Recall that the client CLT is the variable that becomes instantiated with the PID of the sender of the message when the pattern match succeeds. Sending is done by this exclamation mark that is the send operator in Erlang. Once the message is sent, the server loops again and increments the total number of requests. The case of multiplication works identically, except for two differences. The first one is that we denote the multiplication operation using the tag mul, and the second is that the result of the computation is obtained using the multiplication operator star rather than plus. Same as the case for add, we loop again. The final pattern here matches stop requests that clients send when they wish to terminate the server. The message consists of the client PID, and now the payload is simply the atom stop. What does the server do when it pattern matches? This receive clause body simply sends a message to the client consisting of a pair with the tag by and the total number of serviced requests. Note that unlike the previous cases of add and multiplication, the stop case does not loop. And what this does is that it terminates the server process naturally. Let us try running our calculator program now. Here I'm using the Mac terminal, but you could use Linux or WSL if you wish. I am currently located in the root directory of detector. If you forgot how the detector directories are structured, you can refer to the tutorial website, where the directory structure may be found under the Setting Up Detector section. Okay, so let me cd to the Erlang directory examples like so, and then go ahead with compiling the Erlang source code files included. To compile, we can use the prepackaged makefile just to simplify things. Now that the build has completed, I'm left with a new directory called eben that includes all the compiled files with the beam extension. And just for your information, the beam format is an intermediate code, similar to class files in Java, okay? And this beam code is interpreted on the Erlang virtual machine. We can go ahead now and launch the Erlang shell by typing ERL and include the eben directory from our compilation to load the binaries that we have compiled in the shell code path. Okay, so we can see now that the shell has loaded, and now to launch the calculator server process, we invoke the calc server start function. If you remember from our previous section, calc server start accepts one argument n, which we use to track the number of requests the calculator server handles. Also, start spawns the calculator server loop to execute as an independent process and returns the PID. We need to keep hold of this PID in order to use it when communicating with our calculator server, as we shall see shortly. So, let us launch the calculator server now by typing pid equals calc server start 0. There we go. This launches the server and stores the PID into the variable pid. Now remember to terminate every expression written on the Erlang shell with a full stop, otherwise it will not run. Anyway, so the result we get back from start is the PID, which is a unique triplet of integers that is assigned to processes by the Erlang virtual machine when these are spawned. Let us check whether the server has indeed started. And we do this by using the isProcessAlive built-in function. We type the following and use the variable PID as an argument. Good, that returns true. So now it's time to calculate some stuff and test the server out. I want to try an addition request first. We do this by typing PID and an exclamation mark, followed by the message we want to send to PID. If you recall, add requests consist of pairs where the first element is the PID of the sender and the second is the operation we would like the server to perform. To obtain the PID of the shell process, which we'll need to include in our request, we make use of this built-in function self. So let us type pid exclamation mark and construct a new tuple with 2 elements. The first element of this pair is the PID of the shell, which we get from self. And the second element is yet another tuple, that is the payload. Let us go ahead now and fill the payload that consists of the atom or tag add and the 2 numbers we want added, in this case say 10 and 97. Now send expressions in Erlang evaluate to the message that is to be sent. In this example here, it evaluates to this tuple that we see on the shell. Behind the scenes, the message is deposited in the mailbox of the calculator server that, in turn, handles it and sends its reply to the Erlang shell. How do we take out messages from the mailbox of the Erlang shell? Well, we use this function flush. And as you can see, we get back our reply consisting of the pair tagged with OK and the result of our addition. Okay, so let's move on to test the multiplication now. Once again, we type PID followed by the send operator followed by the message. We dump the mailbox of the Erlang shell to the terminal, and as we can see, we get the result of our multiplication. Finally, let us terminate the server. And how do we do this? We simply send a stop request following the same steps as before. So, we type the send expression, and now the payload consists of the atom STP. Now that we executed the send expression, let us just confirm that the calculator server has indeed exited. We simply use once more the isProcessAlive function, which in this case returns false. All that remains is to flush the mailbox and confirm that we have received the reply from our calculator server. And yes, the reply is the pair tagged with by and the total number of requests handled by our server. So I will close the shell by typing Q and return back to finishing our discussion on the calculator server example. So the behavior of the calculator server we have just seen on the shell can be described as a state transition model. And this state transition model, shown on the right, captures the visible program events that the calculator server can exhibit while it is executing. It abstracts away from the internal details of our server process loop, here on the left. For instance, this transition model does not show how the variable tot keeps track of the total number of requests by incrementing them using plus. In fact, it will turn out that for our purposes, we are not interested in capturing such a level of detail. Rather, we are interested in the communication events that the calculator server can exhibit when it interacts with other client processes. Okay, so much like our Erlang implementation on the left, this transition model depicts three possible interactions that the server can perform starting from its initial state Q0. For instance, the receive clause for add here corresponds to the transition starting from Q0 and going to Q1. The action that the server performs on this transition is a receive event, which we denote by the question mark symbol in our model. In reply to this receive event, the server transitions from Q1 back to its initial state Q0 and exhibits the send program event in the process. As an aside, Q1 here intuitively describes the state at which the server currently is. We are able to tell what the server is doing, but only by peeking at the Erlang code. For instance, the server has a step where it prepares the reply tuple consisting of the tag OK and the calculation A plus B before sending this tuple to the client. But this kind of information is not captured in the model. Okay, let me get back to our explanation. So program events such as send and receive include the data associated with the events. In this example, the event data consists of the processes involved in the interaction, which are the server and the client, and also the messages that are exchanged between them. There are other events that detector supports, such as process exits, but I'm going to once again ask you to refer to the tutorial website for more details. As we shall learn in part 2 of this tutorial, event data is extremely important since it enables us to perform very specific reasoning on the process interactions. The multiplication scenario is almost identical to the case I've just discussed for it, so I'll go ahead and skip that. Let's focus on the stop. So in the case of stop, the model transitions from Q0 to Q3 when it receives the stop request from a client. Subsequently, it transitions to the final state Q4, denoting server termination. One question that should come to mind at this point would be, so how do we know whether the server behavior modeled as the transition system on the right is correct? And we attempt to answer such a question in the rest of this tutorial. What does the transition system being correct mean? Since the transition system captures the operation of the program, we might as well ask, what does our program being correct mean? Well, actually it means that the program is correct with respect to certain properties. There are a number of properties we would like our calculator server program to respect. The tutorial website lists a small selection of such properties. Let's have a quick look at them. For example, the server loop does not control the initial value of the parameter n that the function calcServerStart accepts. We could therefore require that the calculator server total request count is never negative. Another property that we would expect is that server replies are always sent to the client indicated in the request. Yet another property we want to hold would be a request forwarding two numbers always returns their sum. These properties have something in common. They frame the correctness requirement as a guarantee that the program must always provide. Such properties are called safety properties, since they stipulate that for any sort of behavior that the program can do, nothing bad ever happens. As a consequence of this condition, showing that a program violates a safety property entails finding just one instance of a program execution that exhibits bad behavior. In fact, producing this evidence is enough of a proof that the program we are examining is not safe with respect to the property in question. In Detector, we can specify such safety properties. We will learn how to do just that in the second part of the tutorial. Okay, so we have seen an example program in Erlang that interacts with clients via messages. This program we shall use to drive our tutorial. We also interacted with our program from the Erlang shell, and in the process, familiarized ourselves with the basics of Erlang. Our program was also described abstractly via a transition system that captures its behavior. And we concluded with a sample list of properties we would want our program to observe.